All right, I'll get started then. Hi, my name's Chris. I work at Formation, mostly on machine learning stuff. And in this talk, I'm going to talk a little bit about some work we did earlier this year on some C++ and Haskell bindings. This is all joint work with some really good people that I'm really happy to be working with. Unfortunately, the library at the moment is not open source, but it's been on our to-do list for a while, so if there's interest, I think we could get it out pretty quickly. Just come talk to me afterwards. This talk's mainly going to be about some of the tools for writing C and C++ bindings in Haskell and some of the concerns that you might want to address. The library in question is a machine learning library in C++, but I've tried to keep the ML specific details to a reasonable minimum, so it should be fairly generalizable. So at work we deal mainly with two classes of machine learning problem. One is recommender systems, and the second is contextual bandits. And for contextual bandits, which are a certain kind of specialized form of reinforcement learning, we use a lot of Wabbit. Wabbit is a little bit like TensorFlow in the sense that it's primarily a gradient descent engine, but it's several years older than TensorFlow and a little bit more constrained in the sense it doesn't allow user-defined functions. There's no backprop algorithm in it. Instead, it takes some fairly simple regressors and through this sort of series of reductions, it can build up more complex machine learning models. And I'll talk a little bit about what that means in a moment. The main interface is old school. It's just a command line. And you use the CLI to configure either batch jobs or to set up VW to run as a daemon. And here I'm setting it up, if you can see, to train a one against all multi-class classifier on 4 classes. That's what the -OAA4 means. And then I'm consuming a training data file in probs.dat. And then what VW is going to do is just step line by line through that file, taking gradient steps, reading in the features, making an output prediction, testing the prediction against the actual label. And then every 2 to the I steps, it's printing out a short update. And then at the end, it's giving a summary report. The outputs themselves are probability vectors, in this case, associated with the likelihood of a given feature set belonging to one of the 4 classes. So if I just grab the tail of the actual training data, the tail command's cut off there, but I'm just looking at the last 5 labels of the training data file. And you can see that the labels are 1, 1, 2, 2, 1. And then the outputs from VW are 4 vectors. And it looks like the first 4 vector is incorrect by maximum likelihood. It misses class 1 barely. And then the latter 4 are correct. If I'd taken the head of this file instead of the tail, I almost certainly would have gotten much worse results because it's a gradient descent engine. It just steps through and learns as it goes, and it's just doing 1 pass. Under the hood, what's happening is because there are 4 classes, VW is actually spinning up 4 separate classifiers in a one against all fashion. So the first classifier is going to just try and, it's a binary classifier. It'll separate class 1 from the rest and so forth. And then each classifier itself is then reduced to a regressor. And so this is the function doing that last reduction from classification to regression. And it's making a separate call to that base learner, which in this case is a regressor. And it'll call that base learner's either learn or prediction function, depending on how it's configured. And these learn and prediction functions are the main 2 actions, at least that we'll want to think about in this talk, which means we're going to need bindings for them in Haskell. We'll also need to be able to read the result of the prediction back out of VW. And you can see that the chosen labels actually sort of idiosyncratically stored in the example struct itself. It's also important for performance in this case that both the learner and the example are passed by reference. So this is critical because a complex learner like a contextual bandit is going to actually generate a bunch of sub-learners, which are then themselves going to generate sub-sub-learners and so forth. And so you have a whole bunch of models all reading from the same example buffer. Oh, I should say one more thing about that. It's doing what I might call some like idiosyncratic VW error handling. So the return type of the function is, what is it, void? So it's not a pure function, and the error handling is it's just print statements, right? So it's doing some rudimentary sort of type checking on the label. If the label's what it's expecting, great. If not, you get a fun message. So we'd like to fix that, constrain it somehow. And sorry, I'm probably going to mix up C and C++ a lot in this talk. I generally mean C++. So inline C is the main tool we used. So it's a Haskell library that lets you pretty seamlessly intermix C or C++ libraries and embed C, C++ code in Haskell. No, it's from FP Complete. But it's very nice. And you can pass data from code in either language with pretty minimal overhead. It relies pretty heavily on template Haskell. So template Haskell, if you don't know, it's an extension to the core language that allows for compile time metaprogramming. So you can directly convert back and forth between concrete Haskell syntax and the underlying AST. So somewhat similar to Lisp's macro system. And we also have a little bit of C++ code stored in that header file, mostly exception handling and wrappers for the VW functions we want to use. So the main interface to inline C is a collection of quasi-quoters for inlining C code. And a quasi-quoter is essentially a function which takes a string to a template Haskell AST. So they're part of template Haskell, and they make it possible to write custom parsers. The Oxford brackets there, the square bracket followed by a bar, those are sort of indicative of quasi-quoters. And in this case, you'll see there's like a square bracket and then one of the inline C quasi-quoters, and then a pipe. The return type of the actual C could be a function, could be an expression, could be a block, depends on the quasi-quoter, and then the actual C code. And every expression of this sort corresponds to a C, or I should say C++ function. So here's a typical example using an expression quasi-quoter. So this is just making a cosine function, and it's expecting a C expression because it's an exp quasi-quoter. One thing that this is doing that you might not expect is injecting a Haskell value into the C function. So it's not just pulling a C value out, it's putting a Haskell value in. And the way it's doing that is using what's called an anti-quoter. So quasi-quoters pull C values into Haskell, anti-quoters put Haskell values into C, and you can note the quasi-quoter by the presence of that dollar sign. And so every quasi-quotation is going to be an argument to some C function. So this is an example of how that's actually used in our library. So here's our bindings for the predict function that you saw earlier in the predictor learn function in VW. So we're using here a custom anti-quoter called a with pointer. And the reason we're doing that is because we have these Haskell values, context and example, but they're not really Haskell values in the sense that they're just pointers wrapping void types. And those pointers actually refer to structs that live in VW land that we can't or don't want to copy all the way, but we're doing the bookkeeping for VW. So I need some way of passing those values back and letting VW consume them as pointers to its own data. So that's what the with dash pointer anti-quoter is doing. And I'll talk a little bit more about how that works in a moment. So overall, VW underscore predict returns an int, which is simply an error code. Check is going to handle that error code, returning an IO of unit. Yeah.
So were you saying about that there's some data that lives somewhere in C land, and you just want to keep the index to it or something over on Haskell site, you not actually want the data in Haskell.
Precisely. I want to pull a little bit of data out, and I'll show you exactly what I'm going to pull out in a moment. So here's the actual function that's getting called under the hood. And so you can see the context and the example on the C++ side are void pointers, right? So C++ VW doesn't know where they live, even though they refer to its own example and context structures. So, of course, higher levels of the VW library know exactly where they live, but we're not using those levels. We're just using this stuff. Okay, so one thing I should also apologize for is I'm going to massively overuse the word context, unfortunately, because it's overloaded in this library. So I think there's at least 3 different things that are floating around with the name context. I will try to disambiguate when it occurs. So this first argument here, VW context, it's being statically cast into that VW type, which is then being used. It's predict methods being called. So we could have, in retrospect, probably called this VW underscore VW or VW underscore model or something like that. And then finally, I guess worth noting, we've inserted our own exception handling boundary just prior to the conversion here. So that's what the formation exception does. We don't want to handle every single exception coming out of VW, but we want to handle some of them and sort of parse and segment others. So quite separately, inline C has its own context type, which is probably the most important type in the library, and is basically like a Rosetta Stone for your bindings. And mainly we're going to be concerned with the first 2 fields. So there's a types table, which is simply just maintaining a one-to-one correspondence with C++ types and Haskell types, and then some anti-quoters. So inline C provides a couple of anti-quoters out of the box. They'll allow you to easily use Haskell vectors in C code, C++ code. So the vector len and vec pointer anti-quoters get you the length and pointer to underlying vectors. The vectors need to be storable, so no boxed vectors. Byte string context and byte string pointer serve analogous purposes. In the byte string case, you don't actually have to define what it's pointing to the way that you do with vectors, like at the bottom there. It'll always point to a pointer to char. And that makes sense. It's, I think, a historical quirk that byte strings are not implemented as vectors of chars, but they're isomorphic, or vectors of word 8s in the Haskell case, but they're isomorphic. And then byte string gives you one more anti-quoter just in case you want to null terminate a string and turn it into a C string. And as you can see, contexts are monoids. So I'm going to use that monoid to build up some anti-quotation capabilities for this library. So I'm going to need vector to get that vector context to get probability vectors out. I'm going to need the byte string context to pass command line configuration, or the thing that I had been using at the command line, in, and to also pass data in. And then with pointer is a custom anti-quoter that I mentioned earlier. And we're using that to sort of fool ourselves into thinking that VW models and examples are actually Haskell values, when in fact they're just pointers. So the types table is pretty simple. So I need to get an enum out for the prediction type and for the label type. I'm going to need to define those void pointers, context and example, which on the Haskell side are pointers to void types. So VW apostrophe context and apostrophe example are void types. And then I'm going to have a statistics struct. And in those quasi-quotes on the right, those are from template Haskell. So the T quasi-quote is just for type. And then, as I said, the opaque pointer witnesses, they're void types, so they contain no values, right? They're like empty sets in Hask. And we're only ever going to construct pointers to them because there's no Haskell values other than bottom that have that type. And they're paired with void pointers on the C++ side. So this is a pretty common trick for arbitrarily typed foreign data. And we're never actually going to dereference those pointers, or we can't on the Haskell side because they don't live inside. And then the context itself that we'll be passing around is simply it's that pointer, and then a couple of data fields that we're going to pull out because we're going to use them. So I was going to cut out and do a little bit of coding, but because it took me so long to set up, I think I'm going to push it to the very end. So yeah, all right. So we've wrapped our pointer. Now let's go on and look at the unsafe API. So I actually want to go construct contexts of this type. That's where I'm headed. So a quick primer on pointers, if you don't know. So memory addresses in Haskell are represented as values of type pointer A, where A is some instance of the storable type class. The type argument to pointer A is not actually used, right? The pointer contains an adder hash, where adder is defined in prim. So adder is sort of like the unboxed type associated with a pointer of A in the same way that an int hash is the unboxed type associated with a int in Haskell. And this is kind of nice because it does give us some type safety when it comes to FFI code. So I can't just arbitrarily combine a pointer A with a pointer B. And if A is storable, which it needs to be, then the type tag will tell me what kind of marshalling and unmarshalling to do, the alignment, the stride of the data, and so on and so forth. So the main function, or one of the main functions that's useful for dealing with pointers is alloc A. So alloc A of F simply executes the computation F, which takes a pointer A to IO of B. And in doing so, it will actually allocate a pointer A for F to use. So this sort of works like a local stack variable in another language. And then the memory is freed when F terminates. So we can get lexically scoped allocation of low-level data types. And then with pointer and with pointer underscore are defined in inline C. So they're just helper functions, right? Basically, with pointer just runs alloc A, but then it actually peeks inside the pointer and returns that along with the result in a tuple. And then with pointer underscore, which we're going to use a bunch, actually doesn't look at the result because there's nothing there. It just looks at the pointer. And this is super useful because a lot of C++ code, and in particular VW code, they don't return values. It's always void or cint for errors. So we have to go look inside that pointer because it's going to be updating it with the stuff that we actually want to pull out. And then finally, I'm going to need a custom with pointer type class. So you can see I've defined my example as a new type around the pointer to that void type. And the reason I need a custom type class to use with context and example is because I have to feed that pointer data to the with dash pointer antiquoter I mentioned. And so what is this type class doing? Well, it's like basically spoofing storable. So storable, just to go back one slide, gets used with all these things. And these type signatures, if you're used to like sort of normal Haskell or higher level Haskell, these type signatures don't seem like they make much sense. Like how could you take a function from pointer A to IO of unit and possibly get an IO of A? That seems to violate like Curry-Howard. But under the hood, of course, what's happening is alloc A is giving you a secret pointer A to use. So it's almost like there's this phantom pointer A on the left-hand side of that type signature. Of course, if I don't actually have a storable instance, I need that pointer A explicit. And so that's what this with pointer function is doing, is taking PC explicitly. So it's spoofing storable. And I need that because context and example don't implement storable directly, but I still need to use them to keep track of VW models and examples and pass that knowledge back to VW. So how is it getting used? Here's a typical use case. So this is a function that's going to take a line of data called line, and it's going to read it into VW. It's going to pass it to VW, and then it's going to grab a pointer to that data back from VW. So it's using that with pointer underscore function, which under the hood is going to call alloc A for that example pointer. It's going to pass that example pointer directly in the second argument to VW example read. It's already got the context on the VW side, so it's passing, sort of faux passing that context, right? It's passing VW the information to where that context is located. And then we're using those two byte string antiquoters to pass the actual data itself into VW. And then that's all executing. It's returning IO of cint. Check is turning that into an IO of unit, which is exactly what with pointer underscore is expecting. And then with pointer underscore is going to go and look. It's going to peek inside the pointer A and then actually return IO of A. I fmap the example over that, and that's how I get IO of example. And then similarly, when I go to finish an example, now I don't need to pull any more data out. So I'm going to use the with pointer antiquoter twice. And the first one for the context, it's just going to use to figure out which example I'm talking about. And then the second one, it's actually going to deallocate example. And you just have to sort of trust it to not mess with the first one, which is fun. So finally, here's actually how you create new context. So this sort of uses all of these things together. So there's two layers of allocation going on here. Let's start with the innermost one. So I'm using c.with pointers underscore, which I haven't shown you, but it's similar to with pointer. It's just operating on a type family of tuples. And I'm going to pull out the actual context pointer I care about, and then enums for the predict and the label. And then I want to pull out VW's internal representation of its options. So that's what all these options, pointer, and options size, et cetera, are referring to. So I'm going to allocate some memory because I don't know how long that string is. Pull all of that out. And you'll see once I demo this what that actually means. But I'm going to pull all of that out and then create at the bottom the context object. And all of this is masked. So that's what x.mask from control exception. And then if you haven't seen that before, I'll explain what that is in a little bit. OK, so if I were to demo this right now, it would work, but it would be pretty janky. It would be really easy to segfault if you call the wrong thing at the wrong time. It's quite easy to call the wrong getter function. And I'll sort of walk you through some of that later. So it's nice, of course, to not have that. You want to generally be careful with resources, especially if they're large buffers for vectors of features. So what I would like to do is something like this, right? Like I want to read example with a context and a byte string into an example, and then I want to learn and predict on it. And because predict isn't actually returning anything, I need a separate function to go grab the probabilities out. And then I want to finish that. And as long as I pair read example with finish example and don't expose either in the sort of API to the user, that's already going to go a long way to increasing the safety of the library. But it's not great. I can still leak memory because if there's an exception in this code anywhere, then I'm not going to call finish example. How many people are familiar with exceptions in Haskell? OK, quite a few. So I might cut out a little bit early and just sort of live code through some of this to give it more meaning. So like if I were to just do the next simplest, stupidest thing, which is combine all of my actions into one IO, and then try on that, and then pattern match on the result, that would be a pretty obvious thing to do. What would you guys actually do to make this code exception safe? Yeah, bracket. Okay, cool. So I probably don't need to go through the rest of the slides are just what is a bracket, and so on and so forth.
Could you just comment on that? I'm not too familiar with bracket myself.
Yeah, absolutely. What bracket does is it's a pattern that guarantees resource cleanup in the presence of both synchronous and asynchronous exceptions. And under the hood, it uses this function called mask underscore, which you saw briefly in the new context function. And so what mask does is it prevents the runtime system from issuing asynchronous exceptions for a period of time. And so this is really nice, necessary in this case, because we're going to be using this library in a multi-threaded application. So threads can throw asynchronous exceptions to other threads. The runtime the system can throw asynchronous exceptions to everything. However, if I have a higher order function like I do here, which accepts an action it doesn't know anything about, and if that action is really expensive, and I use mask underscore, then I'm going to be blocking for an unknown period of time, which is like really bad manners because there's no thread can stop me. So it's generally good practice to use mask without the underscore. And the way that you do that is mask has a little bit of an interesting type signature. You'll notice it. So it's like existentially quantified IO of A at IO of A, all to IO of B, all to IO of B. And the reason that it has that function signature is it sort of gets used like this. I mask on the outside, and then I'm going to pass this restore function to the same code that I had before. Now, restore has type signature, that innermost type signature, for all A, IO of A to IO of A. And the reason it's existentially quantified is because restore has to eat any action. It has no idea what action it's going to eat. So it has to guarantee that for any IO of A, it can still give you back an IO of A, which means it can't really mess with the A. It can only do sort of IO of unit type stuff. And in this case, it's just restoring the ability of the runtime to issue asynchronous exceptions. And this is nice. However, we're not actually trying to catch exceptions and do any sort of logic in particular besides cleanup. So if all we're interested in doing is cleanup, resource deallocation, and so forth, then we're much better off just using bracket. And so what bracket is, and it's really not just a function, it's like a pattern. You see bracket for all sorts of different resources, but they all generally follow the same pattern, which is they'll accept like a before function, which allocates the resource, gives you an IO of A, an after function, which deallocates it, and then the action itself. And then it's just going to call mask with a restore, and then give you the resource, let you compute on it, but it's going to force you to do that with asynchronous exceptions on. And then if there is an exception, either synchronous or asynchronous, it will clean up, and if there isn't, it will clean up. So that's bracket in a nutshell, and I can use that here much more safely, right? So now I can just use my read example and my finish example as part of a bracket, and in fact I can do the same thing at the context level, right? So no need to let contexts float around themselves either, and so that gets me pretty far. So I have a little bit of data here that's coming from the same file that you saw. Can you all see that? That better? Okay, so if I look at, I haven't actually shown you what the data itself looks like. So it looks like that. So this is VW's input format, which is a close derivative of libsvms. So it's got the actual label here, and then a vertical bar, a namespace, and then a whole bunch of features. So the features are, in this case, they're numbers. These could be arbitrary strings, and followed by a colon, followed by some floating point number, or an integer, or nothing. So I've got some data, and then I can create a context. So let's say new context. And I need to hand it some options before I do that. And so my options are the same ones that I was showing you early on in that slide. So it's a one against all classifier with 4 classes. It's a logistic regressor. And now I can actually go ahead and look at that context. And sure enough, it's got those types that I showed you earlier. So it's a pointer to some address in memory, an output type, an input type, and then that option string, which was such a pain to pull out. And this is its internal representation of its options, which looks a lot like the options I fed it, but with some extra stuff, some assumptions it's making. And so I can do things like get statistics, because that was part of my types table. And of course, I haven't used it for anything yet, so it's not very much interesting there, other than min label and max label, which are sort of, for mysterious reasons, initialized to -50 and 50, even though this is a logistic regressor. But that's VW for you. And now I can say read an example. So if you remember read example, X, I need actual data to pass it. So I've got a bunch of examples. Let me just grab the first one. Now if I look at X, you can see again it's just a pointer to some word in memory that VW had allocated, but I'm tracking. And now I can start using it. So I have like a predict function. I have a learn function. And because I'm working with a multi-class classifier and I'm pulling out probabilities, I have like get multi-class probs prediction, I believe, which is just going to grab an example and pull out that vector of floats. So I can go ahead and use all this like so. I'll learn on my context an example, and then I can sort of combine that IO action with a predict. And I combine that with and I need to feed the example to that, and out comes my vector of probabilities. So that's nice, like it's working. It's still not great because like my user could easily use the wrong getter function, like this, and VW is still giving me information. Get multi-class prediction returns a word 32. The reason VW does that, I think, is because there is a scalar valued getter defined in this configuration, get cost sensitive prediction, which returns an actual double that means something. And then I guess I assume VW is just taking this string and casting it into a word because it contains the same digits, which is slightly horrifying. So you definitely don't want that. That's fairly easy to constrain, of course, because you're actually getting the types out of VW that it's expecting. So it's pretty easy to go ahead and like define a new unsafe VW that requires the user to at least explicitly say what the label type and the predict type they're putting in should be. Of course, they could still use the wrong function even if they do that. So it's not foolproof. You need some sort of type class or type family solution on top of this to constrain which configurations go with which getter functions. The other interesting thing about this is, so it looks like I just learned on this thing, and if I were to learn again, it would seem to be, overfitting, right? It's getting even more sure that the first class is the right one. But if I call get statistics on my context, oops, what happened? Anyone? Why is it still 0 everywhere? I'm supposed to be learning, right? See, nothing. So what I have to do is call finish example. And now I've learned one time, right? It's seen one example, even though I actually ran this command 3 times, and each time you saw, the probability that it's class 1 go up. So I've sort of cheated VW here in the sense that it thought it saw one example, but I actually hit learn predict 3 times. So that's bad. I really don't want that. So that's where bracketing can help you. If you don't surface finish example and read example to the user, it's impossible for them to do that. So I think I'll give you guys maybe one more little fun mess, and then sort of open it up for questions. So I'd like to at least just run over the same list of examples that you saw in the CLI early on. I'll take my with example function, and if you can see this, I'm just going to loop over a list of byte strings, and then for each byte string, pass it into with example. All right, so with examples has a type that's pretty similar to with example. But it's just taking a list of byte strings instead of a single one and returning a list of outputs instead of a single one. So now I can do something like with unsafe VW, and I can pass it my options and a label type and a predict type, scalars. And I can pass it a function from a context to, let's see, I want to do with examples of my examples, and my context. Can you see what I'm typing? And what else? I'll just use the same learn and predict action. So learn, predict, context. So that type checks. And I think I actually want, well, yeah, let's run that and see what happens. Yay, okay. And I suppose I could prove to you that these are actually probability vectors. Let's see, I need to fold L prime. I think there's one in there. So let's just add these up. And nice. So that's well within reasonable tolerance. So it looks like it's generating things that sum to 1, which is good because they're supposed to be probabilities. However, this library is still, I think, not safe. And some of this is just the limits of Haskell in general. And if any of you have an idea of how to fix this, I'd be interested. But because I'm letting my user pass in actions, there's certainly nothing to stop them from, you can imagine a user coming in and wanting to, let's say, be a little more point-free and folding the example into the reader applicative, like so. So I claim that this has the exact same type signature as learn predict. Let's confirm that that's true. Learn predict prime. So it's a function from context to example to IAO, a vector of floats. Just like learn predict. But what will happen if I call this function with learn predict prime? Anyone? Yeah, that's right. This is going to segfault. How can that possibly be? It has exactly the same type signature as learn predict, which performs completely correctly. So what gives? So the problem is laziness. So under the hood, I'm actually using the reader applicative now, not the IO applicative. And because I'm using these half TIE fighters, under the hood, there's a const function, which is consuming those IO actions. And because const is an eager, it's not actually executing the IO actions, which means learn predict prime is not learning, it's not predicting, and then it's attempting to pull something out of an illegal address, which causes it to segfault. Which is really too bad because it seems like it has the right type signature. In fact, it does have the right type signature. So I suppose one way to get around this is to expose strict primitives and force the user to just use those to construct their action functions. So that's it in a nutshell. I can talk a little bit about some of the safety and performance issues. So clearly the API is still pretty loose. Users can segfault even with using what appear to be the right functions, at least from a type perspective. There's a notion of a model missing to handle configuration more securely. And then, of course, inputs, data inputs and options are still, at least in this talk, both unstructured byte strings, which is not ideal. In terms of performance, these bindings are about 20% slower on average than the CLI, optimized CLI, at least on our main use case, which is contextual bandits. That makes sense to me because every time it reads an example, it needs to read it into the Haskell runtime, allocate a pointer for it, give that pointer to VW, pass the example to VW, read the results into the pointer, and then grab the results back. So there's a lot of extra memory management going on that is very difficult to get around. However, in this case, the added safety, at least for us, is worth the trade-off because we can create a concurrent library on top of this. Mainly, we're concerned with serving predictions to multiple threads quickly, so we can do that with STM. And that's it. Yeah. So thanks for listening.